Welcome to this video about self-descriptive distributed automation environments. A self-described distributed automation environment consists of file devices and control devices on the file and shop floor level. On the ID level we have programs like engineering tools, monitoring and control applications such as HMI or SCADA systems, data storage and data analyzing tools, message routing, software and others. The layer for self-descriptive automation provides services and tools to interact horizontally and vertically in a dynamic and ad hoc way. In this video you will see how this works with nxtControl and by the strict usage of available standards. The shop floor consists of three IEC 61499 runtime environments with file level items connected with Ethernet. On the ID level we use NXT Studio for the system configuration, nxtHMI for control and monitoring, Unity for 3D process simulation and the XMPP client to receive routed messages. The IEC 61499 runtime system was extended with capabilities to support multicast DNS implementing the Avahi API, XMPP client with serverless communication extension and UDP raw socket communication to simplify the demonstration. The IEC 61499 runtime is located on our nxtDCS Mini evaluation and reference hardware. We will switch now to the live demo. Open the project and the system view. The demo uses free controller as the distributed environment. Each controller instantiates a service manager to propagate the controller as a self-described automation device. Application services are also propagated through the MDNS interface. The Service Manager function block is internally a network between the Service Discovery interface, the device descriptive storage. The function block consists now of all the information that it is needed for the device discovery itself. Let's also look into a function block or into the function block which is holding the information for application service. An application service function block consists of the function block network of the HMI interface, the service discovery interface, the service connection interface and the service configuration itself. All of these function blocks are used on the one side for discovering the service and on the other side to establish the connection to the raw UDP socket connection if the service is needed from one of the applications in the automation environment. With the services discovered, we can now have a look into the application level of our demonstrator. The demonstrator application is a distributed conveyor and robot application. A single application object is represented by a single function block. The function blocks have adapter interfaces to build the application program within the controller. The adapter interface connects the function blocks together to build the automation application, to create the combined device self-description and to allow other application interfaces to connect to the object such as routing resolvers or workstation applications. The controllers itself work independent of each other. This means also that we have three independent applications running on our IEC 61499 controllers, which we will use to demonstrate the service-oriented approach in distributed automation. A top-level function block in the application represents a real-world object. Each application object function block For example, for a conveyor, generates the part of the service self-description that relates to itself. The object uses configuration data given by the user through the HMI, data resulting from the application structure within a single controller, or statistical data coming from the type definition. The partly generated self-description will be registered into device self-description storage as soon as the application gets deployed and started. All 3 controllers will be deployed with its application. As soon as the application gets started, the device description storage gets created and is available for the device discovery service. The deployment process will download all the function blocks made for the application and will do all the initialization and startup stuff. The deployment can be started from the system's device management view, and all the deployment is done in parallel to all controllers in the shop floor. If we look into the details of the results, we will get an impression of the data within the self-description file. We will start to publish the first controller's device description now. Unity will read the self-description information and build up the layout of the application as a result. Each function block of the application gets discovered and gets its representation within the Unity 3D visualization layout. The same will be done for the second and the third device. To better recognize the different domains, each controller has its own color in the model. The color for sure is part of the self-description information. Also, more complex structures of an application can get easily recognized by the 3D simulation layout, and all the objects are created normally. Also, if we now stop the publishing service, Unity will automatically remove the objects from the model and add it again as soon as it finds the service with the device description on the network. So let's look into the details of the discovery process. To look into the details, we will start in console application, which monitors all the signals flowing on the network. We republish the services of one controller and see what happens. As soon as we start the publishing, the controller appears on the network and starts to exchange the information with other devices also located on this network environment. The discovery process starts by publishing the IEC 64099 device discovery service as a multicast DNS record. Unity or any other interested application registers a multicast DNS and starts to browse for this service. In our demonstrator, the IEC 64099 device discovery service defines an XMPP serverless client connection endpoint. XMPP is used to exchange the self-description information between interested parties. As a first message, we ask the device for supported features. The device answers with available features and details for a certain feature. In our example, we have the feature to communicate with dynamically created IEC 64099 adapter connections. As a second feature, we can query the device for mechatronical objects. Unity is interested in the mechatronical objects to build the model, so it sends a message to get all the mechatronical objects self-description information. The device answers with information for each mechatronical object, which has registered itself during the startup phase of the device. After Unity has all the information read out, and as we have announced a service for dynamic IEC 64099 adapter connections, we can start the communication between the Unity engine and the controllers to simulate the model and interact between the Unity 3D model and the control application. Let's have a look to the available settings which can be modified out from the HMI, which directly modify the self-description information of an object. The values are set through the HMI interface and used by the device description generator to build the self-description information. The self-description is built by an algorithm which reads all the information provided and builds the device description information as a structure of XML statements. These statements are used in the device itself to register the device and propagate the device description itself to the network. The service manager is used to enable or disable the service propagation of a device. On the demonstrator, this can also be done through the HMI by starting or stopping published services through the HMI interface. In our test environment, this allows to easily simulate and check all the functionality on our distributed environment and how it works in combination with foreign applications. So, what happens if we need to extend an application? Let's start from the existing application. As we have seen before, we have mapped this application to a controller and reflected the application itself to the Unity environment, where we discover the devices, build up the application and have a direct mapping from the applications view to the Unity environment's simulation engine. The application directly reflects to the environment of Unity. To extend the application, we go back into the application environment of the studio. Now we simply duplicate a conveyor object and wire it to the application. After that, we assign it to a controller and deploy the controller again, so that all our modifications are recognized by the controller and the application is updated with our new object. To do that, we simply start the deploy command of NXT Studio and update our controller with the new application. After the deployment has finished, the object is available on the controller for operation. If we restart the publishing service, we see the new object already added to the model with its default settings. It's now the orange object in the upper corner here. With the HMI, we adjust the parameters for the instance and reconfigure the self-description information. For that, we need to open NXT Studio and redesign our HMI application so that we have available the newly created object also on the HMI display, so that we can open the environment and modify the settings of the object. After we have added the object in our canvas, we just redeploy also our HMI to have them available in the runtime view of the HMI viewer. As soon as we have the HMI available, we can directly start and use it to modify our settings of our newly created object. For example, we modify the position and the coordinates where the object resides. We can also adjust additional settings, for example the direction of the conveyor, which will get directly reflected in the 3D model of the Unity simulation environment. We save and apply the new settings to our configuration and recreate the self-description configuration in our controller. If we now republish the information of our controller in the network, we will see that the newly object resides now in the model at that position what we have configured. Now we can adjust again some settings, for example the color of our object, to reflect and modify the conveyor object to our needs. As soon again as we modify the position and republish the information, for example we use the color from other objects for this controller and modify it in our environment, we publish it and reconfigure the object. We republish the information after recreation, and we will see that this directly is reflected in our 3D model of Unity. Let's go to the simulation part. The Unity model uses the dynamic adapter communication to exchange model data with the controller's automation program. Every time a controller publishes its configuration, Unity detects this on the environment and creates the model based on the available device self-description. Each controller publishes or removes its self-description independently. The Unity model is completely controlled by the automation controllers. The control logic for starting and stopping of belt drives is located in the controllers. The Unity environment is used to detect collisions of the simulated objects. In our example, we have light barriers as part of the conveyor. When we put objects in the model onto the conveyor, light barriers get detected and the informations are forwarded to the controller. The program controls the belts and avoids collisions of parts on the belts itself. As each controller works independently, objects will stop at the edge of a controller's environment. In our example, the controller domains are illustrated by different colors. If we put additional objects onto the conveyor line, the belts get controlled by the program logic, but prevent collisions of the items on the belts. We have also noticed application services at the beginning. As we know, the controllers work independent of each other, but they provide application services to be used from foreign controllers. In our example, parts of the conveyor line stop at the boundary of the first controller because there is no information about free space to move on. Other controllers can publish their application service to the network, and an interested controller can browse for may needed services. In our example, the first controller is interested for conveyor application service. The other controllers can publish their conveyor application service to the network. We publish this service by going into the NXT Studio, opening our application and fire an event to publish the service. The service will immediately appear on the list of available services in the HMI. We do the same for the second controller. Now we can select one of the published services to be used by the first controller. We select and load the service, which allows our parts to move on. As soon as we have loaded the service, the controller knows about the free space on the next controller's conveyor line and therefore can start to move items on the new connected conveyor line. After we have finished our work, we can unload the service again and parts will stop at the edge of the controller's implementation. New parts on the conveyor line move normally as long as they reach the border of the controller. There they stop again because no service is loaded at this time, and so the control logic stops the parts at this edge. A summary what we have seen in the demonstrator. We have seen how we can generate self-description information out from 4099 applications. We have seen how we can use multicast DNS service to propagate services in automation environments. We have seen how we can use XMPP to exchange messages for self-descripted devices. We have seen how Unity can use self-descripted device information to build dynamically 3D models that can interact with the control application in real time by the support of dynamic 4099 adapter connections. And we have seen how we can load propagated services and use them in the independently operated automation environment. Thank you for watching this video.